Hello and welcome to a CNCM lecture. We will be talking about dynamic programming in math competitions, and I am Eli Park. So first let's introduce this topic. So by Wikipedia definition, dynamic programming is both a mathematical optimization and a computer programming method. So it's generally used in computer science, but basically, so some problems, they split into subproblems where we have to compute a similar problem, and then we like split it up all the way down until we reach a base case. A general visualization could look like this, and then it like branches off into like smaller problems, and then they branch off into smaller problems, and then this just like goes down all the way until we reach a bunch of base cases, and then which bring us all back up to the main case. So recursively, we can solve these kind of problems straightforward, where we just like take the top and then we split it into these cases, and then split more cases and split more cases, and etc. However, in dynamic programming, we optimize this by solving smaller cases first. So we solve the bottom cases, and then we build up until we can get these larger cases, which are a lot easier. So, how do we apply this to math competitions? No, we're not going to be coding an actual program. We're going to see in this handout with a few examples. Again, it's not necessary to be familiar with dynamic programming beforehand. And also, just a little side note, if you see DP, this is often dynamic programming, obviously depending on context. So let's take a look at our first example. It's a generic problem. So find a number of paths that go from the bottom left tile to the top right square. Moves can only be made up or right one square and travel over obstacle and cannot travel, sorry, that should say and cannot travel over the obstacles marked in X. So let's first see here. Generally it's natural for our first step to be, oh okay, so we're starting here. Well, we can make two moves, up and right. So it seems sort of natural to split into these two cases. So maybe one case goes through this tile and another goes through this tile. And then that means we're going to have to split it further into cases. So if we investigate the case where we start here, then again it could go up or it could go to the right. And then if we investigate the orange case here, we could also go to the up or to the right. And then this case where it starts going a ton. You can see how many cases, well, not how many cases exactly, but the large amount of cases that are necessary in order for us to keep going. And it's just going to be very painful to keep doing this. And some optimizations are going to have to be made. Sorry. We already see from the little casework we just described, the path that goes up right and the path that goes right up, they both land in the same square. So meaning that any path that the number of paths that start from here and go to here is the same as the number of paths that start from here and go to here, because they're literally the same. So that means that we can make a little bit of an optimization. So if we label these, if we let A0, A1, and A2 be the number of paths that go through those squares, instead of having to do casework on A0, A1, A1, and A2, we can just do A0 plus 2A1 plus A2, meaning we only have to find 3 more cases. So there's already a glaring optimization that we can make here. So furthering our casework, we can extend this. So we have up to B0, B1, and B2. So notice that the square B0 is only obtainable by one path. From here, just up, up, up. But then B1, however, can be obtained in 3 paths. B1 can go up through A1 and then to B1, up right to A1 and then B1, right up to A1 again and up to B1. So in other words, since B1 can be reachable from both A1 and A0, the one path that goes through A0 contributes 1, and then the 2 paths that go through A1 also go through B1. So there's 1 plus 2 equals 3 paths that go to B1. Similarly, there are 3 passes that go to B2, so we can say that the answer we're looking for is also equal to B0 plus 3B1 plus 3B2. This is a lot easier than 7 separate cases. We have 3 separate cases. But we start to think, okay, so we start to notice a little pattern. Okay, so if we consider a particular square, right, the number of paths, so like here we just noticed, and if we consider a particular square, the number of paths that seem to go through it is equal to the sum of the number of paths of the square that go directly left of it, so this one, and the one directly below it. If we add the number of paths that go through these two squares, it seems that they add up to the number of paths that go through here. And it's actually obviously true, if you take a moment to think about it. So we can start so we can actually start creating an algorithm to find our answer much easier. I make the claim that the number of paths that go through a square is the sum of the number of paths that go through the square below and to the left of it, if they exist. So we start by labeling the bottom left corner with a 1, okay? And that means that these two squares, we consider what these two squares are going to have. Well, there's nothing to the left of it, and then one below it has a 1, so they both take 1s. And then we consider this square. We see that this one, there's nothing to the left of it, but a 1 below it, so it's 1 plus 0 is 1. Here, there's a 1 to the left of it and 1 below it, so 1 plus 1 is 2. Here, there's a 1 to the left of it and nothing below it, so it's just 1. So we keep adding up in this way, and then next here, naturally, we're going to get the 1, 3, 3. And then you're going to see that these are exactly the coefficients we were talking about, 1, 3, and 3 here. So we can actually just extend this. We can keep working this out. So if I just take a moment to fill this out, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 6, 3, these are going to be 0, 1, 1, 6, 9, 3, 2, 7, 15, obstacle 3, 9, 22, 15, 3, 31, 30, oops, sorry, 37, 37, 18, 68, and 55, and then our answer is going to be 123. So let's check that. Yep, our answer matches. So our answer is going to be there are 103 passes that go from this bottom left to the top right. Just as a final remark, I just wanted to say that I intentionally tossed in some barriers, this x through 3 x's here. When there are no barriers, there's actually a nice bijection relating to the Pascal's triangle, and there's obviously a nice closed form considering there's Pascal's triangle. You can read about more of that if you look up a northeast lattice path. I believe you will be able to find more about that, but it's outside the topic of dynamic programming in general, so we're not going to be discussing it further. So next example. So let's look at 2019 AIME problem 2. AIME 2 problem 12. So for n greater than or equal to 1, call a finite sequence a1, a2, all the way to an of positive integers progressive if a of I is less than a of I plus 1, and a of I divides a of I plus 1 for all 1 is less than or equal to I is less than or equal to n minus 1. So find a number of progressive sequences such that the sum of the terms in the sequence is equal to 360. So brute force on this solution, unlike the last problem, is actually viable, meaning it's not completely like out of hand. When a similar problem was featured back in 2017, my team actually brute forced it during the Duke Math meet. However, there are much greater optimizations that can be made. So let's let d of x be the number of progressive sequences that have some x and do not start with 1, okay? So if the first term of a particular sequence is x, right? So let's say a of 1 is equal to x, then everything else has to be divisible by x, right? So that means that a of 2 is going to be equal to some constant times x, and then all the way to a of n is going to equal to some constant times x, right? So that means that if we divide it all by x, then this becomes 1, this becomes c2, this becomes all the way to cn, right? So the sum of this should be equal to 360 divided by x. And then if we kill out this 1, right, then we can see that we can, the answer that we want is, so if we kill out the 1, then we get a -1 here. So the answer that we want is the sum of all x that divides 360 of, I apologize, that was written poorly. X divides 360 of d of 360 over x minus 1. This is the answer that we want to get, because if we iterate over all possible values of a1, which we are calling x, then we can kill the a1 value, divide everything by x, kill the a1 value, and then find smaller progressive sequences of smaller sums. Okay, so sorry. So now if I can expand this out, because there are a non-large amount of divisors of 360, we can just write this all out. Writing it all out, we get this is equal to d of 359 plus d of 179 plus d of 119 plus d of 89 plus d of 71 plus d of 59 plus d of 44 plus d of 39 plus d of 35 plus d of 29 plus d of 23 plus d of 19 plus d of 17 plus d of 14 plus d of 11 plus d of 9 plus d of 8 plus d of 7 plus d of 5 plus d of 4 plus d of 3 plus d of 2 plus d of 1 plus d of 0. I had a cheat sheet in front of me, so I'm just copying it down. But basically, these are all 24. If we consider all 24 all 24 divisors of 360, then we just take d of 360 over x minus 1, where x is that divisor. And you can verify, you can count out that there are 24 d of somethings here, verifying that we've covered each one. So here, it's actually fairly easy to see that for each prime integer, p, d of p is going to equal 1. As there's only one possible sequence, right? It's just a sequence p, where it's the first and only term is p. So that means it's because we can't have terms that start with 1 by definition of d. It's also easy to see that d of 1 is going to be equal to 0, because that first term is going to have to be 1, but we're not allowed to have that. And d of 0 is going to be equal to 1, just the empty sequence. So if we consider that, then we can actually do a lot of simplification. We can kill d of 359 is going to turn to 1. So that's going to turn to a 1. That's prime, 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 prime. Oh, no, that's not the prime, sorry. 4 is not prime. Prime, prime. D of 1 is nothing. D of 0 is 1. So, yeah, so if I fill those in with a bunch of red ones, I could do that right now. Then we're going to get that this actually simplifies. If we all add up all these ones, then we can simplify this into d of 119 plus d of 44 plus d of 39 plus d of 35 plus d of 14 plus d of 9 plus d of 8 plus d of 4 plus 15. These were the number of prime and zeros that we had. Sorry, why did I just erase all that? I accidentally erased all that. That was silly. Just advance 20 seconds on this video. Okay, so now we're done writing. So now we need to start computing each of these again by using the same way that we split up the d of 300. That we split up, try to find the number of ways of 360. Okay, so well, we need to consider. We want to start from the smallest one, okay, and then we're gonna actually keep a little table slash. Actually, I'll make it a little smaller, but we're gonna keep a little table on this side of some values that we've already computed. Okay. So first, let's start with calculating d of 4. Well, how many of these sequences add up to 4 that don't have first term 1? Well, if the first term can't be 1, right, then it has to be, if the first term can't be 1, then the first term has to be either 2, wait, actually, no, it can't even be 2. We consider all divisors of 4 that are not 1, okay? And those are all the possible first values, so, and then we just do d of 4 over x minus 1, where x is that divisor. So yeah, plugging that in, we're going to get those two divisors that are possible are 2 and 4, which yield us d of 1 plus d of 0. We know that d of 1 is 0 and d of 0 is 1, so we get 1 here. So we can save on the top, we can actually, I'm just going to keep this at the bottom. D of 4 equals 1. This is going to be useful later. Splitting up d of 8 similarly, we're going to get d of 3 plus d of 1 plus d of 0. 3 and 0 both yield 1 and 1 yields 0, so this gives us 2. So actually, I'm not going to write this here. I'm actually going to erase this one because we already have it written here. But we're going to save some other local values that we're going to see. D of 9. This splits into d of 2 plus d of 0. Also gives us 2. So now d of 14, this is where we get d of 6 plus d of 1 plus d of 0. So this is now where it becomes not immediately obvious what this is already, because we don't know what d of 6 is. We have to compute this again. D of 6. D of 6, we're going to split this into the divisors, the non-1 divisors are 2, 3, and 6, so we're going to get that this is going to be equal to d of 2 plus d of 1 plus d of 0, which is equal to 2. So we're going to save this in our little table down here. D of 6 is equal to 2. So using this value, we get that d of 6 plus d of 1 plus d of 0 is 3, because 2 plus 0 plus 1 is 3. So now, we split d of 35 into d of 6. Hey, we already computed that. D of 4. Oh yeah, we computed that too. And d of 0. So this is where the beauty of dynamic programming shines. So we've already computed d of 6 and d of 4. Had we had bashed this out, we would have to recompute this again. And since we aren't considering, if we were bashing, we aren't really considering the multiples, this becomes very tedious. But we already pre-computed this. D of 6 is 2, D of 4 is 1, and D of 0 is 1. So this is going to be 4. Next, for D of 39, we're going to get that this is going to be D of 12 plus D of 2 plus D of 0. So now we're going to actually have to compute D of 12 because we don't know what that is. d of 12 is equal to, the non-1 divisors are 2, 3, 4, 6, 12. So we're going to get d of 5 plus d of 3 plus d of 2. That's not a 2, whatever. D of 1 plus d of 0. 5, 3, 2 are all prime. D of 0 is going to give us 1. This is going to give us nothing, so we're going to get 4 here. Sorry, not 4, for that. D of 12 is 4, I apologize. D of 12 is going to give us 4. So I'm going to write this down on the side. And then this gives us 4 plus 1 plus 1 is 6, so D of 39 is 6. And then we go to D of 44. D of 44 is going to equal D of 21 plus D of 10 plus D of 3 plus D of 0. So at this point, this is really just bashing, but we have to find, but it's not as big of a bash as compared to just like brute forcing. So we need to find D of 21. We're starting to notice a little pattern about D of P times Q. It's going to be equal to D of P minus 1 plus D of Q minus 1 plus D of 0. So that's the thing. So maybe you can use that to find D of 21 and D of 10 faster. But we're going to go on to the next slide for the sake of space to find D of 21 and D of 10. D of 21 equals D of 6 plus D of 2 plus D of 0. Again, we found D of 6. This is 2. Our pre-computations are shining. So D of 21 is equal to 4. So now we need to find D of 10. D of 10 is equal to D of 4 plus D of 1 plus D of 0. Again, we've found D of 4 already. D of 4 is equal to 1. So 1 plus 0 plus 1. D of 10 is equal to 2. So using these computed values, 4, 2, 1, 1 is going to give us 8. So now lastly, we move on to D of 119, which is equal to D of 16 plus D of 6, which we found, plus D of 0, which we already know. So now we just need to find D of 16, which I will do on this slide. D of 16 is equal to D of 7 plus D of 3 plus D of 1 plus D of 0. 7 and 3 are prime. D of 1 gives us 0, and D of 0 gives us 1. So D of 16 is equal to 13. I'm sorry, 3. So this gives us 3. D of 6, which we know is 2, and D of 0 is 1. So this gives us 6. So now we've actually computed all of these values. So now I remember that our answer that we wanted is just like this on the side. So plugging these all in together, we just need to find what 6, sorry, let me do this in a different color. We need to find what 6 plus 8 plus 6 plus 4 plus 3 plus 2 plus 2 plus 1 plus 15 is. From quick computations, give us that this answer is going to be equal to 47. That is our answer. But yeah. Summary. So dynamic programming is an optimization method generally used in recursive problems, as you've seen, where we calculate a particular small case and reuse the calculation for larger cases, which yield our answer. So many times, dynamic programming is not going to be immediately obvious. You're gonna have to do some work or to actually implement dynamic programming and save some of the computations that you would have done over and over again. So yeah. Yeah, thanks for watching. Join CNCM in the Discord link in the description. Also, please subscribe to our YouTube channel. If you are watching this on May 29th or after, then the 5 problem of the days is May 29th, 2021, that is. The 5 problems used as our problem of the days will also be released in the handout, which you can find in, again, the description below. And for those of you who are watching before that, please attempt our problem of the days. They're good practices to use this topic. And without further ado, we will end this lecture. Thank you guys for watching again. This is Eli Park.